Bipolar junction transistors. There are many types of transistors. Bipolar junction transistors are called BJTs for short, are the most common. So when we talk about a transistor, we are referring to a BJT. Other types of transistors will be referred to their complete name, like MOSFETs or JFETs, or etc. So if we compare a diode to a transistor, what we start with, a diode has a PN junction, which is a P-doped material and N-doped material, and it has the creates the function of a diode. The P is for positive, that's the anode, and N is for negative, and that's the cathode. So some guy looked at this and said, well, what happens if we add another doped material, an N-doped onto it, and we have two junctions, we have an NPN. Well, when they did that, they realized that they had some special characteristics. They called it a transistor. So we have our collector, our base, and emitter. And that's an NPN transistor for NPN. Transistors look like this. There's the 2N3904. You've seen that in the lab. Someone else said, hey, if I got a PN junction here and I put another P-doped material on the bottom, what happens? Well, so they made a PNP, and that becomes a PNP transistor. PNP transistors are usually used in negative power supplies. So we'll be concentrating on NPN, which is like 90% of the time you'll be dealing with an NPN transistor. We're also going to see this type of methodology where they say, well, we started with a material with just a PN junction. We'll add another one, get an NPN. Let's reverse it. We'll put PNP. We'll find out that other transistors, they'll add more junctions on. So interestingly, a transistor is a current control device. The base current, IB, controls the collector current. So we have a base current flowing in from the base to the emitter, and that's going to control our collector current that goes from the collector to the emitter. So there's a relationship. It's called beta. Beta is the specification of a transistor. And what happens is the collector current is equal to beta times the base current. So when we put a little bit of base current in, we're going to control a lot of collector current out. A 2N3904, which is the standard that we use in the lab, has a typical beta of 100. And typical, we'll see a little bit later that it might be 100, might not be. So a little bit of base current controls a lot of collector current. So typical base current is like 100 microamps to 10 milliamps. A typical collector current is from 100 milliamps to 10 amps. So I kind of like this picture. It shows different types of case styles and transistors. So a 2N3904 is down here. It's a small signal transistor, and it'll typically have somewhere 100 to 400 or 500 microamps of current in the base, and it'll control somewhere around 10 to 100 milliamps. The more current we control, the bigger the device. So a device like this, a TO3 package, or I'm not sure what that one is, but this will have a base current will be maybe 100 milliamps or 1 amp, and it'll control 10 or maybe 50 amps on the collector. So bigger the device, more current it can handle. Here's I kind of like this one also because it's relative size. So we have a small 2N3904, a big TO3. We have some surface mount transistors, which are super small. Emitter current. The emitter current down here, IE, is a combination of both the base current and the collector current. Now what happens is the base current is so small, it's typically 1/100th the value of the collector current, that we can actually say that the collector current is roughly equal to the emitter current. A transistor is two circuits. We treat it like two circuits. We have the base emitter circuit, and we deal with the base current. And then we have the collector emitter current, a circuit. So the collector emitter, and we have this side which deals with the collector current. We treat each circuit as a separate series circuit. So we have our base emitter circuit with our base current, and then we have our collector emitter circuit, and we deal with the collector current. Base circuit. The base circuit is a series circuit. We're interested in the base current and the base emitter voltage across here. This is going to act just like a diode. It's going to be 0.7 volts. So we're going to treat it just like a diode. If we start with 12 volts, and we drop 0.7 volts across here, what we'll find out what's left over is going to be across R1. So 12 minus 0.7 is 11.3 volts. We know what our resistor value is, 33K, so if we use Ohm's law, the base current will be equal to the voltage across the resistor divided by the resistance, and it'll give us 342 microamps. Notice that we don't even care what's going on the collector side here in the emitter. All we care about is this current going this direction. Collector emitter circuit, it is a series circuit also. It starts with our supply. Supply is normally called VCC in the transistor world, or VS for supply. We'll call it. We have 12 volts here, and we have our collector current flowing down this way. Now what happens is the transistor collector emitter junction acts like a switch, right? When it's open, the transistor is off. When it's closed, the transistor is on. We call it saturated or saturation, right? So I like to think of it, you got your ON there for saturation, and that, so closed, the transistor is on. When we have base current that's zero, no base current flowing, we'll get no collector current. So the collector current is controlled from the base current. When we have a base current that's flowing, the collector current is equal to beta times the base current. The collector emitter junction is not perfect when the transistor is on, so it's turned on, it's saturated. There's a voltage across the collector emitter junction called VCE sat. So this is our saturation voltage across here. So it's not a perfect switch. The switch closes and then we get a voltage across here. Typically, VCE sat is 0.2 volts. We can determine the maximum current that this circuit can handle, and this is based on the transistor. So we look at our Q1 and it has a beta of 100. That's from the spec. We look at our base current is 342 microamps. We figured that out earlier. So the maximum collector current that this transistor can put through it is beta times the base current. So it's 100 times 342 microamps. That means that the maximum current that this transistor can flow in this circuit is 34.2 milliamps. So we can provide 34.2 milliamps to a load that's hooked up. This would be our load here. This could be, it's a resistor, an LED, it could be a relay, it could be a motor, it could be all sorts of things here. So this transistor can, in this circuit, can provide a maximum of 34.2 milliamps. We want to figure out the circuit's collector current. We have some components in here that are going to limit the current. So R2's job is actually to limit the current so we don't blow this LED, right? So we know the transistor's beta is 100. We looked up the spec for the LED. It said a forward voltage of 1.8 volts when it's on. We know that the saturation voltage across VCE sat is going to be about 0.2 volts. So if we know it's 0.2 volts here, 1.8 volt here, we should be able to figure out the voltage across R2. So we start with 12 volts. We subtract the forward voltage of the LED, 1.8 volts. Then we subtract the voltage of VCE sat, 0.2, and that's the voltage across the collector emitter. So when we do that, we end up with 10 volts across R2. Well, the voltage that's left over is going to be across R2, right? So VR2 is 12 volts minus the forward voltage of the LED, VCE sat, and we end up with 10 volts. Since we know the voltage across R2, we know what the resistor value is. Using Ohm's law, we can figure out the current going through the IR2. Now the current going through IR2, because it's a series circuit, is going to be the same current that's going through the collector. So we end up 10 volts divided by 1K. We're going to get 10 milliamps flowing through, which will turn on that LED. The LED will turn on. So, big question, is the collector current less than IC max that we figured out, right? We want to make sure, does this circuit work? Well, the collector current was 10 milliamps. IC max is 34.2 milliamps. That's how much power or current the transistor can supply, and 10 milliamps is less, so this circuit will work perfectly fine. This ends this section. Next section, we're going to start talking about beta, the problems with beta, and biasing transistors.